Greetings. I've been thinking about the statistical mechanics of binding and realize after having written down the states and weights for several of these genetic regulatory problems that I may have left in my wake some confusion about the reconciliation between the statistical mechanical view of binding and the thermodynamic view of binding. And to be very concrete about it, here I'm reminding you of when we use statistical mechanics to look at binding, where we were very explicit in the model we made of the binding. And what I mean by that is that we imagined our universe to be a box that had a bunch of lattice sites. We had omega such lattice sites, and on those omega lattice sites we distributed L ligands, and then we had this receptor which I show you in green. And working out the statistical mechanics of this led us to this expression, which I show you here, forgetting for the moment the red pieces. Okay, so this is our version of the Langmuir binding for statistical mechanics. And then what I want you to then also recall is that earlier we had written down the classic Langmuir form, which is shown right here. And that we got from thermodynamic arguments. So this brief vignette is I want to talk about the reconciliation of the thermodynamic view of binding and the statistical mechanics view of binding. So that's what we're about in this little vignette. Okay, so we've already, implicitly, everything is already there. And in fact, I think I even concretely said the things that should be said, but I want to be more deliberate about it. So the thermodynamic view gave us a dependence on the concentration of ligand, which I represent by these square brackets, L square brackets, and what we found was the classic Langmuir form, which I show you here, which sometimes people will refer to also as Michaelis-Menten form. So that's what I plotted up here. That's also what I wrote up here. And if you go back to your notes, what you will see is that this is what came out of basically recalling that the KD is defined as the concentration of ligand, the concentration of receptor over the concentration of ligand receptor pairs. That's where that all came from. Then the statistical mechanical viewpoint what we ended up obtaining was P bound, and this is of the number of ligands, was equal to L over omega e to the minus beta delta epsilon over 1 plus L over omega e to the minus beta delta epsilon. Let me add another page here. So we have these two impressions of binding, which are now both on the screen. And what I claim is that they describe the same thing. They describe precisely the same thing, but in order for that to be true, I need to move from the language of numbers. So this latter guy is in the language of numbers of molecules. And in terms of binding energies. Because you'll recall that delta epsilon was epsilon bound minus epsilon solution. You'll also recall that beta was 1 over kBt. Okay, so the thing I want to point out now is, let's go back to our lattice model. So we have this lattice of omega sites, and it's decorated with some number of ligands, which I drew in red. So we have some L ligands. And now just to put a few labels on here. So omega is the number of lattice sites. L is the number of ligands. And one last quantity that I want to define is that little volume. Little v is the volume of one lattice site. Okay, in light of all that, now I'm going to be a little bit more, as I said before, a little bit more deliberate about what I did rather quickly when we were talking about binding. And that is to say, well, okay, if I were to do my favorite pastime, which is multiplying by 1, I could put a little v here and a little v here and a little v here and a little v there. That's the equivalent of multiplying those two, the numerator and the denominator, by 1. So that's good. But now we recall or note that the number divided by omega v is the number divided by the total volume. And that's what we know of as the concentration. So far, I see then that I have concentration L over 1 over little v, and then e to the minus beta delta epsilon, and that's over 1 plus the same thing. Let me move this down the page. So this is our expression for p bound now. And now if you notice that I have this quantity 1 over little v. What does that mean? That means one molecule for every little volume little v. So what does that correspond to? That corresponds to essentially having the entire lattice filled up. So let's look at that. So I need to restore my lattice sites, and then this 1 per little v corresponds to this density. This is a little bit laborious to draw all these, but this is the concentration L0. If those, okay, if little v is approximately 1 nanometer cubed, that implies that L0 is 1 per nanometer cubed, which is the same as 10 to the 9th per micron cubed, which is 1 molar. So the standard state concentration, what I'm calling L0, corresponds to 1 molar, which corresponds to 1 molecule per every nanometer cubed box. So far, now we can keep drilling down. We've got P bound is equal to L over L0, e to the minus beta delta epsilon over 1 plus L over L0, e to the minus beta delta epsilon. And finally, I'm going to define Kd as L0, e to the beta delta epsilon. That's our final insight on this problem. Now let's just review. Remember, if Kd is smaller, that means that the concentration it takes to get to half saturation is smaller. Let's look at the curve here. So note, Kd here is the concentration at which we get to half saturation. So if Kd gets smaller, that means that the molecule binds more tightly, more easily to the receptor. So that means stronger binding, and indeed, if you look at this, my definition of Kd it says that, so first of all, delta epsilon is negative. Well, how do I know that? Because epsilon B is less than epsilon solution. It's an advantage to bind to the receptor. So the more negative this thing becomes, here I have something that's less than 1, right? Because I have e to the minus a quantity. So that's clearly smaller than 1. So what we're doing is we're finding that we're going to modulate L0 by this factor, which is going to move us to the left. So stronger binding corresponds to more negative delta epsilon, which corresponds to smaller KD. So that was the point of this little mini side vignette, which was essentially just kind of a refinement on something that we did earlier, and it was just to point out, how to reconcile these two views of binding, one of which is based on thermodynamics and involves concentrations and KDs, and the other of which is based on statistical mechanics and reckons things in terms of number of ligands, number of latticytes, and binding energies. And what we've seen is how to reconcile those two things in the form of this statistical mechanical expression for the KD, which brings together the macroscopic world of KDs and the microscopic world of binding energies in this nice form. So that's what I wanted to say about this stuff.